Hi, I'm Dave Nguyen, CEO of Brain Technology and inventor of the LCPC Transform. In this presentation, I will discuss how the LCPC Transform quantifies 3D tumor shapes, but the same principles apply to measuring 3D signals from PET scans that image light-emitting tracers. To start, let's describe how the LCPC Transform works. In step 1, we extract the outline of a tumor. And in step 2, we define the centroid as the origin of a 360-degree radial grid system. In step 3, this system allows us to calculate the distance of every intersection between the grid line and the object, right, to the center. And then in step 4, we sum the intersections, all intersections on the same radial line into one value. And then in step 5, we then apply the fast Fourier transform to the data in either step 3 or step 4. And this results in a frequency plot, as in step 5, that represents the shape that we began with in step 1. An option in step 6 is to create a single value, a scalar value, to represent the shape that we started with. And a simple way is to sum all the bins, okay, in a frequency plot, or to divide one bin by another bin, as we will do so later in this presentation. To begin, I created two phantom 3D tumors. Here are the consecutive 2D slices ranging from the top of the tumors to the bottom of the tumors. These 2D slices are similar to the outlines of tumors that you would see in a 3D MRI or CT stack. Let's examine one slice in each tumor to see how the LCPC Transform sees them. In the middle column are frequency plots showing how the algorithm sees slice D from tumor 1 or slice D from tumor 2. A simple index can be obtained by dividing the value of bin 2 by the value of bin 3. When we do this, we see in the graph on the right that slice D in tumor 2 has a larger shape magnitude than slice D in tumor 1. Here I said larger shape and not larger size because shape and size are not the same thing, as I will prove later. So using this index called index A, which is dividing bin 2 by bin 3, okay, we can analyze every single slice in a 3D stack. But first, here are the 3D bar plots for each tumor, which is obtained by graphing the frequency plots of each consecutive slice next to each other. Here on the y-axis, tumor A, which is the top of the tumor, is at the front, and tumor H, which is the bottom of the tumor, is in the back. These bar plots are multi-dimensional representations of the 3D tumors that we started with, except they are very cumbersome because there are hundreds of dimensions representing a tumor. However, it is easier for the human mind to see the differences between these two tumors by reducing these bar plots into only 2 dimensions, as seen on the bottom row. We can do this by calculating index A, as we did earlier, for each slice. This results in a bar plot of only 8 dimensions representing each 3D tumor, which is easier to comprehend than hundreds of dimensions. As you can see in the bottom row, the median value of the graph on the left is smaller than the median value of the graph on the right. However, can we make the differences between these two tumors even more comprehensible? That is, what about deriving one value per 3D tumor instead of 8 dimensions? Well, we can do this by summing each of the 8 bars in these graphs into one value. When we do this, we see on the right that there is a 3.6-fold difference in magnitude between tumor 1 and tumor 2. This matches our intuition because the shapes of the tumors are obviously different. Tumor 1 is shaped like a pear, while tumor 2 is shaped like a rounded square. The significance of this 3.6-fold difference becomes evident when we calculate the volume and surface area of these two tumors. Volume shows only a 1.2-fold difference, while surface area shows a very minuscule difference. However, shape, as measured by the LCPC Transform, is distinct from volume and area. Our technology can measure morphological differences that are hidden from volume and surface area. This capability is why brain scanology and its software called Shape Genie will revolutionize medical diagnostics in the coming decades.